Hello everyone, welcome to my video. This is for exam 3 and this is the second video I'm making for this exam. We're going to talk about blood flow and how our blood pressure is manipulated by things like our peripheral resistance and our heart rate, our strength of contraction that our heart makes, and a bunch of other things. So let's get into it. We're going to talk first about the pressure and volume of a cardiac cycle. So in order to describe cardiac cycle and how it affects our blood pressure, we're going to draw a graph. Oh, that's not a straight line at all. I'll draw it this way. So we got an x and y axis. On the x-axis, we're going to put volume. And on the y-axis, we're going to have pressure. And this is going to be volume and pressure within the heart. So I think you have your heart right there. At different points in time between its pumping, it's going to have different amounts or different volumes of blood within it. And it's going to have a different pressure that it's putting on itself as it's squeezing blood out and then relaxing to allow more blood flow to come back in. So this is going to be a graph that kind of explores that whole cycle and the differences in volume and pressure and the relationship that we see there. So pressure, we're going to have a couple of landmarks here. On pressure, I'm going to have on the low end, 10, and pressure is going to be in milliliters of mercury. That's how the body's pressure is usually put in those units. And on the high end, we're going to have 120, which that number should look familiar for your systolic blood pressure, which is the top one. It's usually the bigger number. 120 over 60 or something like that is usually not an uncommon thing to see. Then on the bottom, we're going to have milliliters. We're going to have on the low end 50, on the high end 120. So as you have blood rushing into the heart, when it's relaxed, you're going to have a low pressure, and it's going to fill up. We're trying to fill up the heart with more blood from our veins. So our superior vena cava and our inferior vena cava are pouring blood into the right atrium right there, and we're filling up that volume. And then we're going to begin our contraction. So we're going to see that volume kind of cap off at around 120 milliliters. And then it's going to increase in pressure. As we keep it capped off, we're going to begin contracting that heart. And then we'll go up here. And right when we hit around 120, we're going to open up those valves. We're going to allow blood to flow out of the heart. And so we're going to begin pumping blood back into the body. So we're going to keep our pressure high, but our volume is going to begin to go lower as we're pushing blood back into the body. And then eventually we hit to a certain amount of volume where we're going to drop off that pressure once again. And then we're just going to do the entire thing over and over again. This is essentially how your heart works when it comes to volume and pressure. Notice there's a point in time when your volume is the same, but your pressure is building. And then there's a point in time when your volume is going to be the same, but your pressure is dropping. And that all has to do with the timing of those contractions and the timing of those valves that are opening inside of the heart. All right. So let's talk about a couple of these points that are on these graphs. I'm going to use a different colored marker to make it easier to illustrate what these different corners mean and why they're significant. So this first corner right here that we get to, after we turn the corner, we begin contracting, we increase our pressure in the heart. That first corner is what's called the preload. So the preload is basically you're loading up all that pressure, you have all of this volume and pressure combined to really get ready to squeeze all that blood back into the body with a lot of force, which is good. You don't want too much, but obviously you need some amount of force to get that blood back into the body. So what happens if we lower our preload? Let's say we don't have as much room in the heart as we used to. And this is what happens with a lot of cases where people who begin seeing heart problems when they're a bit older will begin to have less volume to fill up. And we'll talk about why in a moment. Let's say we shorten that. We're still getting up high in pressure, but what happens to the net amount of volume that enters and leaves the heart? So if we have less room for blood, there will be less blood being able to flow in, less blood being able to be capped off, and less blood ultimately being pumped back out into the body, less oxygenated blood. And that would lead to a shortness of breath, fatigue, and in serious conditions, that could lead to things such as like tissue necrosis and maybe even death. So this, in between our lowest and highest volume, is what we call, as physiologists, stroke volume, right? It's also known as our cardiac output. So I'll go ahead and put that as well. So our cardiac output is extremely important, and it's something that a lot of athletes try to increase as they really try and boost their cardiovascular system. Basically, the idea is if you have a higher cardio output, then you're able to oxygenate your blood at a faster rate, which means you're able to do more, with your body. You're able to run for longer, maybe run a bit faster, jump higher, because you're getting that oxygen to those muscles, and you're going to be able to have a much more efficient way to do athletics or whatever you want to do, basically. But if we shorten it, we have less blood that is being cycled through, and the heart isn't able to do its job as well. Now, this can happen for a number of reasons. A really big reasons, especially in the United States, is due to something called congestive heart failure. Now, congestive heart failure is a little bit of an interesting paradox because as you have high blood pressure, which is one of the leading causes of congestive heart failure, is having chronic high blood pressure. That high blood pressure is going to cause the heart to have to work harder. Because if you think about it, I'll draw a very simplified version of the heart right here. So we talked about the cycle of how the heart contracts. So we have blood coming into the right atrium, and it'll flow into the right ventricle. It'll be pushed out of the right ventricle through the pulmonary arteries into the lungs to be oxygenated. It'll come back through the pulmonary veins and flow into the left atrium. Then it will go down into the left ventricle, and from the left ventricle, it needs to be pushed into the aorta to be pumped through the rest of the body. Now, if you have really high blood pressure, it's going to be hard to pump blood from the heart into the rest of the body because the rest of the body already has that high blood pressure. And so the gradient of blood would actually want to come back more than it would want to leave the heart, if that makes sense, right? Because we're trying to pump it, and as we're pumping, our volume is getting lower. And so if our volume is lower in the heart than it is of volume or pressure of blood outside of the heart, then that blood isn't going to want to leave as quickly. And so what our heart will end up doing is it will need to have stronger contractions, and it will have really strong contractions to get the same amount of blood or try to get the same amount of blood out, which would lead to actually your heart muscles thickening. They'll get stronger, which sounds like a good thing until you have this problem. Your heart fibers will get so strong and so thick that they'll actually minimize the amount of space there is left for the blood. So I drew a very thick left ventricle right here, and it's usually on the left ventricle because that's the place where you're having the contractions squeezing into the rest of the body. And you'll get to the point where you aren't able to let in the amount of blood that you need to, and you get this shortening of volume as I have in this graph right here, which ultimately lowers your cardiac output, which is not a good thing. So that is congestive heart failure for you. And obviously there can be some things done. There's heart transplants, there's heart surgeries to try and maybe shave some of that off. There's a number of things that surgeons try to do to lessen this. And of course, the best thing to do is just live a lifestyle that prevents chronic high blood pressure. So the next on the list that we have to talk about is baroreceptor reflex. This reflex, I don't know why, but for some reason it's one of my favorite things to talk about and to think about. I just think it's cool. So I'm erasing the graph that I just drew. We're going to talk about our baroreceptor reflex. Okay, so baroreceptor reflex. I'm going to draw a heart again. I'll draw it in red because I think of hearts in red. Again, I'll just draw a very simplified version. I'm assuming that you guys already know the anatomy of the heart. So I'm not going to draw every single thing on it. But what I am going to draw, what's important for this example, is the aorta. So we got the heart, and I guess that should be coming from the left ventricle, not atrium, right there. So we got the heart and the aortic arch, and off of the aortic arch we have a couple of branches. I'm not going to get into all of the anatomy there, but for the sake of this example, I'm going to kind of enlarge the end of these branches because that's where we have something called our baroreceptors. So I'll draw them in green, just as squiggly lines, so we can see what we're talking about here. So our baroreceptors are going to be inside of our aorta, as well as the major arteries that are branching off of the aortic arch. And what our baroreceptors do is they receive information that basically tells them what our blood pressure is at. So it could be information such as our concentration of salt within our blood, or it could be concentration of oxygen within our blood. It could be a number of things. There's several different types of receptors, but they all do the same thing. They basically essentially read blood pressure. So for this example, we'll just choose salt because I like salty things. So let's say we have our baroreceptor that receives information on how concentration of salt that is flowing through that artery. Now, the less salt that is flowing through, theoretically, that would mean a lower volume of blood or a lower blood pressure. Now, you would see how that would mean low blood pressure, because even if you have not a ton of sodium in your blood, if you have a lot of blood moving through it, you're going to get a higher reading of salt. So that's essentially how it works. Now, if we are noticing there's a lower amount of blood going through our veins, then what's going to happen is we're going to have a set of pathways through our autonomic nervous system. So we're going to have some neurons that will get information from our sensor that will go and synapse with the brainstem, the central nervous system. I'll just put CNS there for us. And then what will happen is, based off of whether it's high blood pressure or low blood pressure, we'll have two different responses. So let's talk about our high blood pressure. Say we are reading high blood pressure. That's like getting really stretched. and the baroreceptor is like, we need to do something about this, otherwise we might, burst an artery. So what happens is we're going to send that neurotransmitter to the central nervous system, and since it's high blood pressure, in order to dilate our veins or our arteries, just to dilate our blood vessels, we're going to have our parasympathetic nervous system be stimulated. And that parasympathetic nervous system will have two effects. First of all, it will inhibit the sympathetic nervous system on the blood vessels, so it will cause vasodilation, so they'll become a little bit wider, which will drop our blood pressure. And then second of all, it will also stimulate the parasympathetic nervous system receptor on the heart, which I believe is our M2 receptor, if I'm not mistaken, M2 or M3. But it will stimulate the parasympathetic nervous system on the heart, which will slow the amount of beats or the heart rate per minute or per unit of time. So that's one example of how our baroreceptors work. The other example would be, say we're reading really low blood pressure, right? Say we're not getting enough blood flow through these arteries. Our baroreceptors will sense that, and they'll synapse with the sympathetic nervous system. So it'll stimulate our sympathetic nervous system, which will then stimulate the beta-1 receptor, which is the sympathetic nervous receptor on our heart, which causes increase of heart rate. It'll also stimulate the alpha-1 receptor on our blood vessels, which will cause vessel constriction, and both of which will affect blood pressure so that it will increase blood pressure. Now, say that we have a horrible accident and one of our limbs is severed from our body. We're going to have a lot of blood loss. We're going to see that blood loss cause, well, assuming that we're not, in complete shock and it's enough blood loss to the point where you're actually losing blood pressure, then this can actually cause what is known as positive feedback, where we're losing blood pressure at a very fast rate. And these baroreceptors will think, oh, we need to increase our heart rate, increase peripheral resistance in order to increase our blood pressure, which works if you don't have a huge hemorrhage happening. If you do have a huge hemorrhage happening, you would have an increase of heart rate, yes, because your sympathetic nervous system would be stimulating that beta-1 receptor, but that would cause positive feedback because you'd essentially just be pumping blood out of your body at a faster rate, which would actually decrease blood pressure, and that would lead to death. So these are good things, but sometimes they can work against you when you're in extreme situations such as that one. And that is baroreceptors. So let's move on to the next topic. Let's see, baroreceptor reflex. We talked about that. Explain the variables that regulate mean arterial pressure. All right, we're going to do another graph because we love graphs in physiology. Graphs and drawings, they're your best friend. So we're going to do another graph right here. We'll have an x and y axis once again, but it will be a little bit different. So on the y axis, we're going to have pressure again. Pressure. And it'll be millimeters of mercury, because that's how we measure the pressure of our body. And then on the x-axis, we're going to have kind of a range of different blood vessels going from largest to smallest. And you'll see what I mean here in a minute. So we'll have, at the very beginning, we'll have large arteries. And we'll just have arteries. And then we'll have arterioles. And then capillaries. I'll just put cap for short. And then at the very end, we'll have venules. So that's kind of like the hierarchy of some blood vessels, going from largest down to smallest. I didn't end up putting veins or anything like that. We're just assuming that we're just looking at the system that's going from the heart to the rest of the body. And so that's what we have. So let's talk about the different pressures that we see within each of these. So at the very beginning, we're going to have kind of a wonky looking graph because we're looking at pressure in these different areas, the continuing to be smaller and smaller diameter of blood vessels. So at the very largest, we're going to have these big squiggly lines going up and down, which makes sense, right? Because your heart is pumping and then relaxing. So there will be moments of higher pressure as the heart is pumping it, and then lower pressure as the heart is relaxing and there isn't as much blood coming out, right? As we get into the arteries, those squiggly lines will begin to get a little bit lower, like that, and this is getting farther away from the source of that pumping, so we're not having as big of those ups and downs. And then by the time we get to the arterioles, we pretty much have just a smooth line that keeps going lower and lower pressure, which this should all be making sense, right? Because you're getting farther and farther away from the source that is causing the pressure, which is your heart and contracting. And then finally, we get down to our capillaries. Our capillaries have a very low pressure. And then when you get to our venules, it's so low that it's actually possible to completely cut off blood flow to these ones. And we'll talk about that here in a minute. But I want to talk about something that we call MAP, M-A-P, which stands for mean arterial pressure. So we have our arteries and their different pressures here. I'm going to draw with the green pen or marker kind of like what that means. So our mean arterial pressure is pretty much, it's exactly what it says it is, right? It's the mean of the pressure. So we're going to start out up here. There will be lots of variability as the heart is pumping. It's more effect, having a greater effect when you're in the larger arteries. It'll have less and less of an effect, pretty much down to the point where our map is essentially the same as what we actually would read at any given point in the very, very small vessels down there. So there's some math that we're going to have to look at in order to really understand these things in blood flow. But when you get down to here, the pressure is so low that in capillaries, you can get as low as 30 millimeters of mercury. That's about 30 right there. And then when you get down to the venules, it can be as low as 10, which is hardly anything at all. In fact, that is so low that if you just, maybe you stand up kind of fast. Have you ever stood up fast and felt yourself get a little dizzy for a second? Well, you probably didn't have any blood flow to those venules in that 1 or 2 seconds where you were feeling a little dizzy. And that can affect certain things like vision. It can also affect the coloring of your skin. If you're putting lots of pressure on a certain part of your skin, you say you have a really tight wristband on, but take it off and you'll notice there's that change of color where it's red around it, but then it's more pale in the middle. That's because there was no blood flow during that time when you were putting pressure on those venules. And that's because the pressure is already so low that it barely exists. And so that one kind of hovers just around between 10 and 0. Our capillaries usually do have enough blood flow to keep themselves going, unless you're starting to wear, restrictive clothing, or say you have a backpack on that's way too tight, then it can cut off blood flow there. But let's talk about why this is important. Okay. So that's this graph. If you need to take a picture, feel free to do so. That's kind of the trend that we see. I'm going to erase it though, and we're going to get down to what goes on between our capillaries and venules and arterioles, because that's really where the bulk of physiology happens. All right, so I drew a picture here. Let's assume that this middle portion with the really small part, like the little tunnel, let's assume that's a capillary. Right? Now, capillaries are really, really small. They're so small, in fact, that they only allow red blood cells through in a single file. So say this is a red blood cell right here. One red blood cell at a time. They can't go two aside, they have to go one aside, can pass through here. And let's say that on our left side, that's the arterial side. And on the right side, we'll have our venule side. So as we are having blood flow through this capillary, we'll have one cell at a time go through from arterial to venule. And capillaries are everywhere in our body. In fact, they are so prominent within our body that your cells at any given point in your body are usually not any farther away from a capillary than 2 or 3 cells. So I drew the second row of cells, or this one other cell right here. We'll just imagine that there's another capillary just below this cell right here. And so you can imagine that that's actually really important because our cells need to be oxygenated, they need to receive those nutrients, and so it's really important that we have capillaries everywhere. So there's going to be a couple of pressures within our capillaries that will affect fluid moving out and fluid moving into them. And this is where physiology gets really fun, because we get to see how little changes can make really big differences within your body. So the first force that we'll be seeing on the arterial side is we're going to have a certain amount of fluid within our blood, and it's going to have a pressure of 30 millimeters of mercury. And you should recognize that number from the graph that we just made before this. And have 30 millimeters of mercury. Now, it makes sense because you have fluid in there. Fluid pushes out on all sides of the capillary, causing a certain amount of pressure, which happens to be 30 millimeters of mercury. And then, as we're going through our capillary is a very thin wall of cells. That's what it's made up of, right? The cells. And they're going to allow certain fluids to come in, and that pressure coming in will add up to 28 millimeters of mercury. So let's assume that this 30 millimeter of mercury pressure on this side is pushing fluid out. And the reason why it does that is for a number of things. There's osmotic pressures at play, so we'll have solutes out here, and the cells will be hungry for a lot of the things that are inside of our blood, such as oxygen, lots of nutrients, things like that. And there will be a certain amount of pressure in our extracellular fluid that will be pushing some of that fluid back into the capillary. But at this point, assuming we're pushing out 30, we're bringing in 28. We're at a net of -2, right? Now, this thing that I drew up here, this is what is the end of a lymph node. I kind of drew a squiggly line at the end because lymph nodes kind of just end like a big tunnel, and they don't have a cap on the end of them. They're open on the end. So we're going to assume that this is open, and they actually have a negative pressure of around -3 millimeters of mercury. We say negative because it acts almost like a vacuum that's just sucking stuff up into the lymph node. And that's why they're kind of known as your garbage system. They kind of help clean out a lot of the stuff that just doesn't need to be there in your body. So we're going to have 30 going out, 28 coming in, another 3, if we assume that it's sucking, right? Another 3 sucking out, we'll assume that that's another 3 coming from our capillary as well. So now we're at a net of -5. So we're losing fluid at this point. And finally, we're also going to have another force where, say, you're exercising, or even if you're just walking, and say at some given point you don't have enough, oxygen to your muscles, then your muscles will have to do anaerobic respiration in order to sustain some amount of strength, even though you aren't pumping enough oxygenated blood to the muscles to get every single fiber the exact oxygen it needs to do every movement that you're requiring it to do. So when you're in anaerobic respiration, your cells, they spit out a lot of byproducts. And a lot of these byproducts will cause more osmotic pressure, more solutes outside of the cell, outside of our capillaries, and that more solute will pull more fluid from our capillary, such as that. And that could get up to around 8 millimeters of mercury. Now, our venules, this is one of the reasons why our venules have such a small pressure, because we're constantly losing fluid through here. And a lot of that fluid is lost due to the amount of cells that are needing to be fed, if you want to look at it that way. And it's also due to these lymph nodes that are sucking up a lot of the fluid and just kind of filtering out all the gunk that gets in there. And so you can really start to understand why our venules are so easily cut off from our blood supply. So, yes. All right, now let's talk about something called edema. Edema is basically just fluid buildup within our tissues. And so usually we have these lymph nodes that are sucking up the extra fluid. There's also some pressure that is allowing that fluid to come back into the capillaries and then through our venules. A lot of the waste products that we end up getting in our blood just due to things we eat, or maybe breaking down like bacteria that maybe were infecting us, just a bunch of things that can happen. All that gunk, like I said earlier, they get swept away through our lymph nodes. And so our lymph nodes are really important because they keep our fluid pressure at the right amount, so we aren't pumping more fluid than we can handle into these tissues. Now, sometimes we can get the end of our lymph nodes capped. And that can happen for a number of reasons. But say for this example, we have some scar tissue that ends up capping the end of our lymph node. And so now we don't have any pressure sucking that extra fluid out. We still have our 30 microliters of fluid coming out. We still have 28 coming in. We still have 8 down here that are coming out whenever we have these extra solutes out here. But we don't have anything to suck away that extra fluid that is left over after the 28 coming back in. So what we're going to see is we're going to see a lot of swelling in the tissue. And this can happen if we have, our lymph node can get capped off. It can also happen, say if we have a normal lymph node, but if we have really high blood pressure and if we have an obstruction somewhere down the blood vessel line. So if we have in our veins, we have some sort of obstruction. If we have like a pulmonary embolism, or if we have congestive heart failure on our right ventricle, so it isn't allowing all the blood from the inferior vena cava to pour into that ventricle. If it gets backed up, then we're going to see more and more pressure build up, and this will have a higher number. Instead of like 7 millimeters of mercury or 8 millimeters of mercury, it'll have like maybe 30 millimeters of mercury, in which case we'll see more fluid being pushed out into the cells, into our tissue, and we're going to get swelling. So that's a really big symptom of congestive heart failure on the right ventricle, is actually swelling in your legs and especially in your ankles and feet. And that's just because gravity will pull that extra fluid that should have gone into your heart, but since your heart is too thick, the muscles are too thick, remember, to not allow enough blood to come in, that blood will become backed up. You'll get a higher pressure on this side. You get more fluid being pushed out into those cells, and that usually happens on the lower extremity just due to gravity. All right, well, that's it for now. Thank you for watching, and see you next week.